Okay, so today we're going to be talking about antiderivatives, and they are exactly what they sound like. It's just the opposite of a derivative. So all we're going to be working on today is figuring out how to take, a derivative in reverse, basically. Okay, so antiderivatives. So whenever we start, we're going to start with a function that is the derivative already. So let me just give you a simple example. Let's say that f prime of x is equal to 2x. Okay, so we want to take a derivative in reverse. So if we want to reverse that right there, f prime of x is equal to 2x, what would we do? All right, so the original function, so now you can see instead of going from f of x to f prime, from the original to the derivative, it's opposite, right? So against the derivative, so other direction. So we're moving from the derivative to the original function, which would be x squared. Very good. So the derivative, and you can always check these. It's really easy to check your antiderivatives and see if you got them right. You just take the derivative and see if you get to the right spot. So if we wanted to check this one right here, we could look at that and say, hey, take the derivative of that, and what do you get? 2x. So it got us back to where we started. So great, right? Almost. That's almost perfect. Okay? There's a small catch here. Okay, and this is one of the most difficult things to remember in the history of mathematics. Okay, when you're working a problem, you will forget this. Just be ready for it. It's going to happen. There has never been a student in the history of my class who has not forgotten this at least once. Okay, at least once. On a test, on a quiz, on some homework, somewhere, you will forget it. And Duncan Watson, y'all know Duncan, my favorite ever. I hope Duncan watches this YouTube video someday. And I'll never forget he had already turned his test in, right? We took a test on antiderivatives. He turned the test in. It's in the basket. And then all of a sudden, out of the, everyone's quiet taking a test. Out of the middle of nowhere, Duncan just screams, "Oh my God, no!" And it was like literally pulling his hair out of his head. And I was like, Duncan, like. But I didn't really have to ask any questions. It was like, man, you need to calm down. But I knew exactly what he had done, right? He forgot plus C, okay? Plus C. You're all looking at me right now like, plus C? What kind of mathematical nonsense is that, right? It's just mathematical nonsense, right? We were using numbers and variables, and there was an x in the original one, so when we got to the antiderivative and there was an x, that made sense, and then you just come and throw a c in there, right? Out of the middle of nowhere, here's a c, okay? Does anybody know what that c stands for, Patrick? Plus a constant. That's exactly right. And we say plus a constant because if we, for example, we're trying to get back to our original. So let me try to set it up this way. Okay? This is what we have right now. We have the derivative, and then we're trying to get back to the original. So let's just imagine that we started with some original function right here, and then we went to the derivative, and now what we're trying to do is, in essence, we're trying to go back to the original, right? So this is our speculation of what the original was. And so this is what we can definitively say. The original had an x squared in it, and that's where it had an x squared in it, and that's where that 2x came from. So this original one had an x squared in it. But after that, we're not really sure, because when you take a derivative, what if there was a plus 3 back here? What would happen when you take the derivative? The plus 3 would go away. Okay, what if there was a plus 5,000 back here? What would happen when you take the derivative? It goes away. And so then what if we were subtracting e squared? What would happen to the e squared? It would go away because it's a what? A constant. And so what we're saying is that when we get down here, okay, and we start trying to take this antiderivative, all we can say with absolute certainty is that there was an x squared, okay? After that, we don't know. There could have been a constant. It could have just been x squared, and there was, the constant's actually a 0. There's nothing else back there. It could have been a pi. It could have been e. It could have been 3. It could have been anything, right? And so what we do in order to symbolize that is we just put plus c down there so that we can say, hey, there could have been a constant along with this as well, okay? So that's what we have. Our antiderivative is going to be f of x. The original function is x squared plus some constant, maybe. And if so, we don't know what it was. Okay, so those are our different possibilities for this. Okay, so let's look at another one. Let's say that I tell you that the change in y with respect to x for some function is 3x squared plus 4x minus 2. Okay, so I'm trying to fill this out a little bit. And so I'm going to say y will be equal to, right? So we have the derivative, and now I'm taking an antiderivative. So, I'm at the change in y with respect to x, that first derivative, and I'm going back to the original function, which is just y now. So can someone tell me, what could we take the derivative of? This is how I always ask them. I ask myself this: what could I take the derivative of to get this right here? What could I take the derivative of to get 3x squared? X cubed. Very good. Plus, what could I take the derivative of to get 4x? Very good. 2x squared. You guys are fast learners. All right, what could I take the derivative of to get 2? 2x. Very good. So to get that negative 2 is 2x. And don't forget plus c, right? So that original equation could have had just some constant by itself there, and when we took the derivative, it disappeared because it was insignificant. But now when we try to go back to the original, we want to say that there is some possibility for it. Okay. Very good on that one. All right, so let's say that f prime of x is equal to x to the negative 1/2. Okay? Go ahead, Jacob.
Is there any way to actually find that constant at the back, or is there just...
Okay, great. So Jacob's question is there any way to actually find the constant? And the answer to that is yes, but you need some information, okay? If they give you 1 point from the original graph and then the derivative, then you can actually go back and find the original equation in its fullness. And we'll discuss how to do that probably tomorrow. If we don't get to it at the end of class today, that's something that we will talk about tomorrow. So we need some value, though, from that original function, and then we can actually find C. Yeah. Okay, so looking at this one right here. Okay, looking at this one right here. What in the world? Two x to the 1/2. Okay, so some people are spitting out f of x is equal to 2x to the 1/2 power, and then plus c, right? Okay, so let's test it. Let's test this. F prime of x. So now we're going to work with this thing we're saying should be the antiderivative. And if we get, if these two things match, then we should be good, okay? So take the derivative, and now the first thing we would do would be multiply by the 1/2. And what happens to the 1/2 and the 2? They cancel. Okay, so there's nothing there, and then it's just x. And when we subtract 1 from the power, we get negative 1/2, and then go away. Okay, so that worked, right? But it just requires a lot of brain power, right? So what we can do is we can actually come up with rules. Okay, we can come up with rules for these antiderivatives in the same way that we came up with rules for a derivative. So let me give you another one right here. Let's say that we are going to try to find, let's just make it 2x raised to the 5th power. Okay, what can we take the derivative of to get 2x to the 5th power? Okay, 2x to the 5th power. Yeah, if you can give me an answer, I'll take one here. Okay, so Cameron is saying that it's 1/3 x to the 6th, and that's right. Okay, that's right. But how in the world did he get that? Okay, well, let's start with what we know. X to the nth power. Okay, if we want to take a derivative, because remember, this is an antiderivative. It's just a derivative in reverse, right? So let's think about what we actually do to take a derivative and see if we can just reverse that process, right? And then we'll be there. Okay, so how do you take the derivative of x to the nth power? All right, so you multiply by the n, and x to the N minus 1. Okay, so there's a very strict process that you adhere to, right? You multiply by the power, in front as with the coefficient of the variable, and then you subtract 1 from the power. Okay, so I'm going to throw a little symbol up here that you guys haven't seen before, but I'm going to put this up here, okay? And I'm going to say x to the nth power dx. And this means take the antiderivative of, okay? So we'll talk more about that and exactly what it means kind of as we go along. But that simply means to take the derivative of something, okay? So whenever I look at this, this right here, and it's telling me to take the antiderivative, okay, I literally want to go in reverse from what we do to get the derivative. So what's the exact opposite, okay, of multiplying and then subtracting 1 from the power? Okay, yeah, so the last thing that we did in the process of taking the derivative was to do what to the power? Subtract 1, right? So if we're going in reverse, then you actually begin at the left. If I told you how to get to the office here and I said, okay, come out of the door and take a right, walk all the way down the hallway, take a left when you get to the end of the hallway, and then the office will be on your right, okay? So that's a right out the door, left at the end of the hallway, right into the office. When you start reversing that and telling me how to get back, what do you begin with? You come out of the office, so you're at the very opposite side, but now instead of, when you came, you took a right to go into the office, but now when you're leaving, you're going to take a left, and then when you get to the hallway, you're going to take a right, and then you're going to take a left to get back in my door, right? So you actually start at the opposite end, okay, and you do the opposite of what you did before. So here we, multiplied and then subtracted 1. So when we're going in reverse, we actually start at the very back, which is where the subtraction happened, but we do the opposite. So that would be to take the power and do what? Add 1. And then we would move forward a step, and that would be where we did this multiplication, right? We multiplied by the power, but now we need to do what? Divide by that power, okay? The power that we now have because we're in reverse, okay? So we're going to divide by n plus 1. Yeah, this does look complicated. Okay, but practically it's really simple, and if you just thought about it long enough, that's what most of you've already been doing in your head. Now we're just actually putting some flesh to what you've already been doing in your mind, right? Okay, so let's try it on this one right here. The first thing we should do is what? Add 1 to the power. So that makes this x to the 6th, and I still have my 2 out front, but now I do what with that new power? Divide by it. So we're going to divide by 6. So I take the 2x, I add 1 to the power, and now I'm just, once I get that new power, I'm simply dividing by it. So f of x, oh, and don't let me forget, right? I will forget during the course of the year, by the way. This is plus c, okay? Plus c. So here, whenever we want to simplify this right here, does everybody see we have the fraction 2/6, okay? And that can just be simplified to 1/3 x to the 6th power plus c. Okay, so 1/3 x to the 6th power plus c. And then we can always test it, right? We can take the derivative and see what we come out with. So if we did f prime of x of this new function that we got, okay, multiply by 6, and that's going to give us what? 6 times 1/3 is 2. X to the 5th, done. And they match, so we're good, right? So we're going in reverse. And it is easier if you have a nice little formula like this right here to use, okay? Yeah. All right, so let's do another one. Let's start with one like this. Let's say that the change in y with respect to x, that first derivative, is just x to the negative 1/4. We'll try to come up with another little rule that will be helpful whenever it comes to these. Okay, so the original function, what's the first thing I do? Add 1 to the power. Very good. So what is negative 1/4 plus 1? Okay, so x to the 3/4 power, and then we're going to divide by 3/4. Very good. Okay, now this just looks funny, right? Now, in the midst of this, don't forget plus c, right? But this does look funny, so I want to change this. Remember, I don't like a fraction within a fraction. So what am I going to do with this major fraction I have right here? Very good. To divide by this fraction right here, we're just going to multiply by the reciprocal, which will be 4/3 plus c. And that just looks funny to me as well. So what I'm going to do is I'm going to move the 4/3 to the front, x to the 3/4 power plus c. Okay, so this is my function, right? So 4/3 x to the 3/4 plus c. We can always test it. Change in y with respect to x. And then if we multiply by 3/4, what happens to those two fractions? They'll cancel, and we just get x to the -1/4, which is what we started with, right? So nice and easy. So here's the big trick, okay? And this is one thing that you'll just kind of do as a shortcut, and it'll help you out a little bit. Whenever you have a fractional power, right? When you get a fractional power, you could just jump straight to multiplying by the reciprocal. So you could actually just skip that step right there. Okay, just skip that. Whenever you have a fractional power, you know you're going to divide by a fraction, and to divide by a fraction is to multiply by the reciprocal. So there's no need to go through both steps, right? You can just kind of go ahead and make that jump if you need to. All right, so let's do another one like that. F prime of x is let's call it 2/3 x to the 1/2 minus x to the 5th plus pi. Normal. Pi? What? Right? Just throwing it in there to make sure we understand what we're doing with it. Yeah, that's correct. Okay, so we'll talk more about properties of antiderivatives and stuff tomorrow a little bit, but it is just like with a derivative. You know, with a derivative, you can just take, you know, if there's a plus sign, then it separates things, and you can just take the derivative of each individual piece. It works the exact same way with antiderivatives. So we just deal with each piece individually. Okay, so that means that our original function f of x would be equal to, what do you do with this? Add 1 to this power, what are we going to get? 3/2. All right, so this 2/3 is already here, right? That was the coefficient that we had. But now that we add 1 to the power, then what should we do? Divide by it, right? But in this case, we're going to be dividing by 2/3. So instead of dividing by 2/3, we can go ahead and multiply by, all right, and I'm going to slide that in the front. I'm going to multiply by 3/2. Sorry, I got that backwards. Yes, I was trying to create one where they would cancel, and I forgot to flip it whenever I did it in my head. So we would multiply by 2/3, and so now that fraction is just going to get worse. But no big deal. Huh? All right, so we got more to go here. So what are we going to have here? This is negative x to the 6th, and then we need to do what? Divide by 6. Yeah. Or, and I'm actually going to do that when I clean it up, Avery. Okay, so we can go ahead and just multiply by 1/6 on the outside. It's the same thing. Yeah. Plus pi x. Very good. The way you get a constant is always just in front of an x. Plus c. Perfect. No. We just need one. If we put a plus c after all of them, Abigail, you could think of it that way, okay? But if I did this and I put a plus c here and a plus c here and a plus c here, okay? Then what could I do with all of those three? If they're all constants, what can you do with them? They're just combined like terms. So what I could do is I could just combine them all into one big C and throw it at the back, right? So there's no need to put multiple constants because in the end, you could just combine them all and make one. Okay, so there's no need to have two. Okay, so let's simplify this thing down. F, not f prime, right? The original f of x is 2 times 2 is 4, 3 times 3 is 9, x to the 3 halves, minus, and I'm going to do what Avery said. This thing's being divided by 6. I think it just looks better if we turn it into 1/6 x to the 6th, plus pi times x plus our constant of integration. Could we have left it like this second, here? Oh, or leave, you're talking about just this individual piece. Could you leave it as x to the 6 over 6? Absolutely, absolutely. But on the AP exam, you're going to see it probably both ways. So I just want you to be able to recognize it, right, in either form. That's all. Okay. What if there's something like a product rule? Okay, so let's say that we had something. It depends on how complex the product rule is. Okay, the more complex it is, it'll take a little while for us to get there. But anytime you have a product rule, you can typically expand it out. So if it was something like that, we would want to expand it. For example, if we had something like this. Yeah, work this with me. This will, because there's sometimes whenever you find one, and it's a lot easier to do antiderivatives. If you just like with derivatives and limits. Remember my rule: you can always simplify before you start. Okay, you can always simplify before you start. So if there's some different forms that you might see some problems in, and simplification just kind of needs to be first thing on your mind, right? Because if I saw this right here before I tried to take an antiderivative, what I would do, right, is just go ahead and actually FOIL it out. So f prime of x is equal to x plus 2 times x plus 2. So f prime of x is going to be x squared plus 4x plus 4. Right? And now, well, this is the same thing. We haven't changed anything, right? The value of it is still exactly the same. It just looks different, but that looking different is a whole lot easier to take the antiderivative of, right? So now if we were trying to go to the original function, what would we get? Very good, right? So, and you'll get better at doing those quickly if you need to. All right, so I'm going to give you another one that's going to be in a form that we want to kind of change a little bit here, okay? Okay, that by itself, right, is not an easy antiderivative, right? Okay, what I'm going to do is, there's a couple of different ways we could attack this, right? But I'm actually going to break this into two separate fractions. Is everybody okay with me breaking this into two separate fractions? So f prime of x is equal to x squared over 2x plus x cubed over 2x, And if you're looking at that and you're like, is that a legal move, right? Is that something that you can actually do? Then just think back to 4th, 5th grade whenever you were doing this. Okay, and you would say that the answer, that is the same thing as 3 plus 1 over 4, which is 4/4, right? Which is 1. You know all that, but the thing I want you to focus on is this right here, right? With this common denominator, we're used to going this way, but it's perfectly legal to move in reverse, right? So we're just going backwards like that. And so now we get a setup like this, and in this one I can actually cancel an x in both spots. And here I'm going to cancel 1. And now the top is squared. So f prime of x is equal to, and I'm going to call this 1/2 x. Is everybody okay with that? Me pulling that fraction off. Plus 1/2 x squared. And now when you're looking at that, you're like, oh, piece of cake, right? No trouble whatsoever. So f prime, or sorry, we have f prime, so f of x will be what? This is going to be x, so 1/2 x. Okay, this is what I'm getting at, f of x. I'm writing down what's already here, 1/2 x. And now I'm going to do what to the power? So this is going to be 2. And then we're going to have to divide by 2, or we could multiply by 1/2. So I'm going to multiply by 1/2 here. Okay, that first 1/2 was already there. That was the coefficient originally there. But then we're multiplying by the 1/2 because of our little rule, for dividing by the exponent. Plus 1/2 x to the third now. And if we're going to multiply, what should we multiply by? 1/3. Good. So that power goes up, and we could divide by 3, or we could multiply by 1/3. Same. And don't forget, plus c. So multiply these together, and we get 1/4 x squared plus 1/6 x cubed plus c. Where was the one I couldn't find? It's probably still there, and I can't find it. Yeah. So Cameron thought it was a good idea to write plus C all over the classroom as a reminder for everyone. So I had to erase my chalkboards every single day because there were just little plus C's hidden all over the place. It's bad. When you're on a test, if you remember it on the last one, you're okay. Because you remember on that last one, you're like, oh, plus C, and you just go back and add it to all the other ones. It's no big deal. But if for some reason, like this, the worst thing is whenever you look at somebody's test and they have it on the first 3 problems, but then like the last 6 they don't have it, and it's like, man, they knew about plus C, and then they just forgot it the rest of the time. And so they lose points for not having plus C all the way down. I usually don't count on, well, if you only did it on one of them, I'll probably just count the whole thing off. But if you have an entire page of really beautiful, perfectly done antiderivatives and no plus C's, then I'll probably just take off a couple of points on each one. On the AP Calculus exam, there are, most of the questions are multiple choice. And so you'll see the plus C. It'll trigger your memory. It's no big deal. But on the free response questions where you have to take an antiderivative, it's really funny. Like if you look at the scoring guidelines, it's like 1 point for the antiderivative itself, and there's a separate point for remembering to write plus C on the AP Calculus exam whenever you look at the scoring guidelines. So it's like they got the antiderivative, give them a point. They remembered to put plus C, give them another point, right? So it actually ends up being worth 2. Right, yeah, so if you don't know how to take the antiderivative, just put some kind of little scribble, scrabble, nothing down there, add a plus C at the back, cash in a point, and keep going, right? Yeah. Okay, now for the most difficult antiderivative that I could possibly give you today. Yeah, they'll get harder as we go along. No point for confusion there, right? That is a 2-point problem right there. 1 point for the EDX, another point for the C. Yeah, so, that one's a really simple one. So I'm not really going to, go over and over and over again that rule like we did the power rule. That one's pretty simple. There's only one rule that I feel like I need to teach you. There's one more rule that I want to get today, and then we'll practice, okay? So f prime of x is equal to x to the negative 1. The rule. No, this we'll get. I don't want to tell you what the name of it is yet. I want to see if somebody can get it before we get somewhere. Now, can anybody tell me what the problem is with this one right here? Okay, well, no sweat, right? If we add a 1, we get x to the 0, and that's no problem, the fact that we have x to the 0, because what is anything to the 0 power? 1. Okay, so that's a 1. Where is the real problem? Okay, that's an issue, right? Something is terribly wrong there whenever we have to divide by 0. So this is a problem. That's not going to work. And it's not that the derivative is undefined for this one, or sorry, that the antiderivative doesn't exist or anything like that. There is an antiderivative for this one, but we have to look at it differently. Okay, we have to look at it differently. Um, f prime of x. How could I rewrite that? Yeah, we could just change the fraction to 1 over x. Now, what do you take the derivative of to get 1 over x? Very good. Plus c. Because the derivative of natural log is 1 over x. Okay? So these two things right here, okay, just have to trigger in your mind natural log. Okay? The absolute value bars, not necessary. You can just put them a parentheses if you want to. It's no big deal. But just remember, you can't take the natural log of a negative number, and so that's why I have my absolute value bars there, because we want a positive value to be able to take a natural log. So that's why those are there. Okay. Tries to trick you with the parentheses or the absolute values. No, it's usually not that big of a deal. Okay. Okay. So I want to make sure that we have a distinction in our mind, okay, between this and this. Yikes. Take away that negative. Sorry. I don't want to like double up on the negatives there. X, and this thing's not calibrated, so it's gonna give me trouble. Um, yeah, this right here is the natural log rule, but it's different from this. Okay, what would you do if you see this? That's exactly what I would do if I saw something like this. I would say that f prime of x is equal to x to the negative 2. And so then f of x would be what? X to the negative 1. And then if we divide by a negative 1, what do we get? Yeah, it'll just be negative x to the negative 1. Okay, and then plus our constant of integration. Okay. What would you do with this one? Move it to the top. So f of x is equal to, yeah, this is going to be x to the negative 3rd when we add 1 to the power. And so now if we divide by negative 3, that's the same thing as multiplying by negative 1/3 plus our constant. Yeah. Okay. So the reason why I'm trying to give you this demonstration so that you can see these two things, right, and these two things, and compare them with these two things. Okay, so here's the big idea that I want you to take away from this. The only one that you can't use the power rule for is x to the negative 1st. Okay, x to the negative 1 power we couldn't do. X to the negative 2nd, it worked. X to the negative 4th, it worked. X to any power other than the negative 1, and so that includes 1 over x, or 1 over x squared, 1 over 4x, right? If our x value would be raised to the negative 1st power, that is the only time that we have to use a natural log. And the reason is because if we actually use the power rule with a negative 1 power, right, we're going to end up dividing by 0, okay? So the only time that we have to use natural log is when we have x to the negative 1, because it's going to cause us to divide by 0. Every other time, any power of x other than negative 1, we want to use the power rule, okay? Want to use the power rule. Let's do a couple of these. We'll stick to the easy ones still, but let me give you f prime of x is equal to cosine x. What can you take the derivative of? This is how I ask myself whenever I'm dealing with trig functions, right? Because you'll get so mixed up going back and forth, okay? Because you say, what can I take the derivative of to get cosine? You say, oh, the derivative of sine is cosine, so there it goes. Now, what can I take the derivative of to get sine? Well, I know that the derivative of cosine is what? Negative sine. So if I want to get positive sine, I need to take the derivative of negative cosine plus c. All right, sine, cosine, what's next? Tangent. All right, so f prime of x is equal to tangent x. Admiral Akbar would be useful here. It's a trap, right? It's a trap. Why is this a trap? What can you take the derivative of and get tangent? There is something, right? Do you know what it is? What is it? It's natural log of cosine. Negative natural log of cosine, because then it'll be 1 over cosine, and the derivative of cosine is negative sine. So it would be negative sine. It's the natural log, okay, the natural log, yikes, natural log, a negative natural log of cosine. Because if you take the derivative of that, you get 1 over the function times, okay, and this thing's still negative, times the derivative, which is negative sine. And so if you multiply those together, you get sine, positive sine over cosine. And sine over cosine is tangent. Okay? Not one I want you to remember. Okay? So my whole point in that, we'll get to that one later and you'll be able to get it by yourself. My whole point in that is that like tangent doesn't work well. Okay? So so we don't want to get stuck with something like that when we're trying to take an antiderivative, at least not yet. Okay? So somebody give me another trig function, set of trig functions, something like that we could actually take the antiderivative of. Okay, that's a good one. Secant x tangent x. And so now the question I'm asking myself is, what could I take the derivative of to get secant x tangent x? Because the derivative of secant is secant tangent. So secant tangent just translates straight to secant. But tangent by itself, there's never a trig function that by itself that we take the derivative of and just get tangent, right? So we got to get funny stuff the rest of the time. These are the only two that are simple. Okay? So what's another one? Okay, so let's take the let's take the antiderivative of secant squared x. What can you take remember, see how I'm asking this question again. What could I take the derivative of to get secant squared? And hopefully your mind will just make the connection for you. The derivative of what is equal to secant squared? That's what we're asking. And the answer is tangent. The derivative of tangent is secant squared. So don't forget the plus c. All right, what's another one? Okay, so f prime of x is equal to negative cosecant cotangent. So, what can I take the derivative of and get negative cosecant cotangent? The derivative of what is negative cosecant cotangent? Cosecant. Sorry, this is not supposed to be f prime of x. Thank you. This is back to the original function, right? So cosecant x plus our constant. All right, so the last one that we haven't done would be negative cosecant squared, okay? So what do we take the derivative of to get negative cosecant squared? Yeah, so the original function is cotangent, right? So these are a little awkward, right? Because, I mean, like I said, these two right here are simple. But when you see this or something like that or like that or like that, it really feels like it should be a very intimidating antiderivative, right? You're like, oh man, like they're being multiplied and that thing's squared, and all kinds of stuff's going on right here, and I'm just really confused. But then if you have to just break it down and ask yourself simply, right? What can I take the derivative of to get secant tangent? Like, oh, that's secant, okay? So the trig functions can be a little tricky because if you see something like this, then they're like, oh, that's nice and simple. No, that is actually really difficult. I would much rather run into this. I'd rather have that than that any day of the week. Okay? Because the first one is actually pretty tough. The second one is extremely easy. Okay? So the trig functions can be a little confusing. You'll look at them and you'll be like, oh man, that's a hard one until you think about it, right? And you're like, oh, no, that one's actually really easy. Okay? So at times, the more simple the trig function, the harder the problem actually is. I don't want to just see cosecant. That's terrible when I see cosecant by itself and I'm trying to take an antiderivative. Much rather see cosecant squared, right? Cameron. Is there such thing as implicit integration? Sure, you could have an implicit function and take an antiderivative of it. But what we'll actually do is called, it's a differential equation, and we'll use separable differential equations to kind of do the opposite of implicit differentiation. But there's a way to get there, okay? Abigail. What do we use antiderivatives for? I don't want to spoil the fun just yet. I will explain that to you probably sometime, I don't know, tomorrow, sometime this week. I will give you the big reveal for what exactly it is that an antiderivative is really used for. Okay? But for now, let's practice. So go ahead and flip in your textbooks. Okay, go ahead and go in your textbooks to page 281. Okay, so page 281 in your text. And I'm going to make this pretty difficult on you. All right, I'm going to give you, what all do I want to give you? Let's go with 1 through 29 odd. Okay, and let me just make this statement real quick. If you look at 11, okay, like one's like 11 on down, when it says, you see this little funny symbol again, right, of 4 minus 18x dx, okay, this right there along with the dx at the back is simply telling you to take an antiderivative. Okay, that's all that means, take an antiderivative. So the antiderivative, what would the antiderivative of this be? Minus. Done. That's number 11, right? It's just telling you to take an antiderivative. There's nothing else to it, okay? Just nice and simple. So don't let those confuse you when you run into those. So you're working 1 through 29 the odd, and then those of you who have the makeup bonus quiz to take, I'm going to let you do that right now, and whatever you don't finish with this will be homework, okay? So go ahead and get started on that.